Let's now focus on the use of selected models for probabilistic modeling of key variables like lot demand and wind speed. In this video, widely used models like the Gaussian mixture model and the Weibull model are studied, included example applications. In modern power systems, the practice of using single Gaussian probabilistic distribution to model lot demand variability is often too simplistic, as it assumes symmetry, unimodality, and light tails. In reality, lot patterns are influenced by time-of-the-day effects, weather, human behavior, and extreme events, leading to skewed, multi-peaked, and heavily tailed distributions. As a result, a single Gaussian might underestimate variability and risk, especially for rare but critical operating conditions. To better capture these complexities, there is a growing trend towards using Gaussian mixture models, abbreviated as GMMs, which represent data as a combination of multiple Gaussian components. Gaussian mixture models can approximate complex multimodal distributions and better reflect real-world variability. However, their use introduces challenges, including model selection, the number of components, parameter estimation, especially because of the risk of overfitting or local optimum, data requirements, and computational burden. Additionally, ensuring interpretability and stability of the model when applied to evolving power system data remains a practical concern. Summarizing, while the Gaussian mixture models offer greater model flexibility, they require careful design and validation to reliably support power system analysis. A Gaussian mixture model P represents a complex probability distribution as a weighted sum of Gaussian components. Mathematically, it expresses the probability density of a variable as a combination of NC Gaussian distributions G, each with its own mean and variance, and a mixing weight that indicates its contribution. Each component captures a different mode or pattern in the data, while the weights Wi, which sum to 1, define how strongly each component influences the overall distribution. This allows the Gaussian mixture model to model multimodal asymmetric and complex data distributions more accurately than a single Gaussian. But how do we obtain these singular curves? Fortunately, many software programs can do the magic for you. For example, the MATLAB function GM distribution can be used to construct the Gaussian mixture model, whereas the MATLAB function fitGMDist can be used to fit the Gaussian mixture model to historical data. Let's see now an example of Gaussian mixture models applied to collected data at Judivana and Punto Fijo substations of one synchronous area of the Venezuelan power system. Note that using a Gaussian mixture model instead of a single Gaussian distribution offers a clear advantage when modeling demand variability at substations like Judivana and Punto Fijo. These systems are influenced by diverse overlapping factors, such as industrial activity, residential usage patterns, tourism fluctuations, and operational irregularities, resulting in non-uniform and multimodal demand profiles. A single Gaussian, with its assumption of symmetry and single pit, cannot adequately capture these complexities. In contrast, a Gaussian mixture model can present multiple underlying demand regimes, like peak versus off-peak, stable versus volatile periods, providing a more realistic and flexible characterization of variability. This leads to improved risk assessment, better anticipation of extreme conditions, and more reliable inputs for probabilistic power flow and operational planning. In short, Gaussian mixture models better reflect the true structure and diversity of demand behavior, making them more suitable for complex real-world substations. The Weibull probability distribution is widely used to model wind speed variability because of its simple yet flexible mathematical form, defined by two parameters: a scale parameter related to the average wind speed and a shape parameter which controls the spread and skewness of the distribution. This structure allows it to adapt to different wind regimes by capturing both low wind speed frequencies and the likelihood of higher wind events. Its suitability comes from the fact that wind speed data is typically non-negative, skewed, and variable over time, characteristics that the Weibull distribution represents well. It can confidently describe the probability of both common operating conditions and less frequent but important higher wind speeds, making it especially useful for wind energy assessment, reliability studies, and probabilistic power flow analysis. In short, the Weibull model balances mathematical simplicity and empirical accuracy, making it a standard and practical choice for representing wind variability across locations. A few plot examples are shown here to illustrate the effect of the shape factor in outlining the Weibull curve for a scale parameter of 1. Notice how a shape factor of unity or less does not even describe a bell curve. A shape factor a bit over unity tends to concentrate the values on the left of the peak, meaning in this location wind speeds are mostly low and the high wind speed have a low probability. A high shape factor of 5 outlines a bell curve slightly skewed to the left. Please consider that all these very distinct curves came from only varying the shape factor only. So, a convenient fitting can be achieved by varying both parameters. To sum up, Gaussian mixture and Weibull models have been explored in this video. It has been shown that a single probability distribution might not be sufficient for modeling the variability of data. That means collecting and checking historical data at a substation. The mathematical definition and fitting of the models has also been explored. Thanks for watching.